So let's look at two more examples. Our first example for this video is solving this equation, and we'll do it in two ways. So I have solution one here. So solution one is how it's done in the book. So we're going to solve for sine of theta. So by the way, this is very, very similar to solving something like this. Okay, so we'd be solving for x here. X is sine of theta, so we're going to solve for sine of theta. So if we send 1 on the other side, we get 2 sine squared is 1. Sine squared is 1/2. So that means taking square roots. Here you have to be careful. If I take the square root, the sign could be plus or minus, okay, the square root of 1/2, which is the same thing as 1 over root 2. And by rationalizing, this is root 2 over 2. So I'm interested in values of sine where sine is either root 2 over 2 or minus root 2 over 2. So I have basically two equations to solve. Or this one. So notice if I would have kept only the positive square root, I would have missed a lot of solutions. Infinitely many, actually. So the first equation to solve, sine of theta equals root 2 over 2. Where does that occur? So trig circle, sine is the y value of a point on the trig circle. Root 2 over 2 is going to occur at pi over 4. But also here, where the y coordinate is also root 2 over 2. That's pi over 4 plus pi over 4 plus pi over 4. That's 3 pi over 4. So pi over 4 and 3 pi over 4. So I've got two solutions here. Theta is pi over 4 or theta is 3 pi over 4, to which I could add any multiple of 2 pi. Doing the same here. Where's the sign minus root 2 over 2? So clearly here and here. So that's an angle of pi plus pi over 4. So that's 5 pi over 4. This is 2 pi minus pi over 4. 7 pi over, I don't know why I wrote 8. 7 pi over 4. So theta is 5 pi over 4 plus 2k pi. And here theta is 7 pi over 4 plus 2k pi. So I can collect all these. So my answer could be all that. Okay, but I want to show you that here it's kind of cute. We can bring them all together in a single answer. So if you look at our answers here, what are the possible angles? Well, there's definitely pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So that's pretty clear because I've just looked at these angles here. So there's clearly those ones. And then we can add 2 pi to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So if we add 2 pi to pi over 4, what do we get? We get 8 pi over 4, that's 2 pi, plus pi over 4, we get 9 pi over 4. So this is by adding 2 pi to this one. If I add 2 pi to this one, I'm going to get the next one here, which is 11 pi over 4. And all of a sudden, I just realized I'm going to get all the odd multiples of pi over 4. Same goes with this angle here. If I subtract 2 pi from it, okay, I'm going to get minus pi over 4. Okay, so I'm also going to get, and same goes with this, I subtract 2 pi. Okay, I'm going to get this one here. So I really get all the odd powers, including negative numbers, of odd multiples, sorry, of pi over 4. So the answer could actually be written like this. Theta is just k pi over 4, where k is any integer. And this regroups them all. So it's kind of nice here to see that this can be written in one single equation. Okay. Notice, by the way, you can also write those your answer. You can write them in degrees as well. So just coming back here, I just forgot to write k is odd. Of course, you can't have even multiples of pi over 4. Okay, so you can also write it in degrees if you like. You could say it's k times 45 degrees, where k is an integer and k is odd. Okay, you could do that. Okay, so similarly here, each of those you could write as, so let's say 5 pi over 4, that's 180 degrees plus 45 degrees. So that's 225 degrees plus k times full rotation, so 360. It probably looks better if I write 360k. But honestly, often when we are dealing with finding all the solutions, in textbooks at least, often they work in radians. So I've seldom seen something written like that. But I mean, it would make sense. Okay, and this would all be in degrees again. So I said I had two solutions. So here's solution 2. Solution 2 is more like, it's closer to the way we'd learn how to solve something like this. So to solve this, I've always taught you to try to factor. And here, if I want to factor this, I could see that, oh, it's a difference of squares. So it's going to give me root a minus b times a plus b. Okay. Well, I can do something similar here. Okay. Except that x is going to be sine. So I've got 2 sine squared theta minus 1 equals 0. So you can think of this as root of 2 sine of theta squared, all that squared, minus 1 squared. So it's a difference of squares. So it's going to be root 2 sine theta minus 1, root 2 sine theta plus 1 equals 0. And then you can equate each bracket to 0, because if a product is 0, each factor can be 0. So either this is going to be 0 or this is going to be 0. And solving for sine of theta, in each case we get sine theta is 1 over root 2, or sine of theta equals minus 1 over root 2. Okay, and then we're back to what we had before. So we're back to here, and then we get all 4 solutions between the interval, on the interval 0 to pi, and then add 2 k pi to those to get all possible solutions. Now that looks more difficult, but by experience, if you factor, you'll never forget like some solutions. Where I often see students, like if they use the other method, right, they solve for sine squared, okay, and at this point they take square roots and then they drop the negative square root. They forget that sine theta could also be minus 1 over root 2, which doesn't occur here. When you factor, it's harder to forget some of the solutions. Okay. Same would happen if, I'm not going to solve it all, but let's say you had to solve cos squared minus cos cube equals 0, okay? It's tempting to do something like this. Cos squared equals cos cube, and then divide by cos squared on both sides. So I've often seen students do something like that. And then they get 1 is cos theta, and then they just solve cos theta equals 1. Where, in fact, there are more solutions than that. If you factor, you're going to see there are actually a lot more. So here we factor, we see, oh, we can factor cos squared, and what remains is cos of is 1 minus cos of theta. And then each bracket, or each factor can be 0. So cos of theta itself could be 0. And then 1 minus cos could be 1. could be 0. So there's also the solution of this equation that would give us solutions, which we sort of lost down the way. And the reason why we lost it down the way on the right-hand side is that by dividing by cos square, we've sort of assumed it was in 0, where in fact it can actually be 0. So by dividing by cos square, we lost information. We only retained in the end this equation to solve, where there are actually 2 equations to solve to get all possible solutions. So it's easier to factor, at least if you don't want to forget any of the solutions. So I won't solve this one. This is just to give you an example where factoring is usually a better way to tackle these problems. We're going to do another one here. Solve 2 cos theta minus 1/3 is cos theta plus a half. So first step is just to group like terms. So we're going to send cos theta on this side to group it with the 2 cos theta. So that's going to give us simply cos theta. And we're going to send the 1/3 on the other side. So that's 1/3 plus a half. So that's 5/6. So we need to solve cos of theta is 5/6. So trig circle, this is 1. So if the cos is 5/6, the x coordinate is 5/6. So we're somewhere here or here. Okay, so clearly there are 2 angles on the interval 0 to pi that actually work. There's this one and then there's this one. But 5/6, I know for a fact this is not the x coordinate of an angle that I know well. Like it's not pi/6, it's not pi/4, it's not pi/3. In fact, using the fact that cos squared plus sine squared equals 1, I could recover the missing y coordinate, but that's not of interest to me here. What I want to point out here is that theta is not going to be a nice angle. Okay, so for theta, I could look at the arc cos of 5/6. Okay, so if I use my calculator, okay, I would get some value. Let's see, let's type that in. So arc cos on my calculator of 5 divided by 6, that's 0.586 roughly. 586. So that's the angle. So half a radian. So I'm in radiant right now. Okay. So if I don't specify, automatically it's in radians. If it's going to be in degrees, I will have to put degrees here. If we don't put anything, it's in radians. Now, if I look at my graph, okay, I have 2 angles. So why am I only getting 1? You have to remember that the arc cos function is going to give you angles between 0 and pi. So this angle here is always going to be between 0 and pi. That's because we chose the that interval so that the cosine function is 1 to 1 on it to define the arc or the inverse cos function. So I get an interval, an angle between 0 and pi, so I'm actually getting the smaller one of the 2. I'm getting this one here. Okay. If I want to get the other one, okay, I have to realize that by symmetry, the other angle is 2 pi minus the arc cosine, minus the angle I found previously, right? So this angle here matches the smaller one above. Okay, so if I subtract the smaller angle from 2 pi, I'm going to get this larger angle here. So what is that? That's let's calculate this. So that's roughly 5.70 radians. Okay. So I've got my solutions in the interval 0 pi. So the possible solutions are theta equals 0.586 radians plus 2k pi, maybe I should put approximately here, or theta is 5.70. Well, now it just looks weird because here I have 3 digits after the decimal, and here I have only 2. So let's put 3. So this is 697. So 697 plus 2 kpi. Like that. So that was an example where the angle is not nice. So we have to use our calculator, and we have to understand what angle our inverse trig function that we use, what angle our calculator gives us. So this is where we have to remember, oh, the angle is always going to be between 0 and pi. On the other hand, like, it's pretty easy to figure out, okay, this is like actually the smallest of the 2 angles that I have on my figure. So even though I don't remember this, I actually know that the angle given here is going to be the smaller one, this one, and then I can use it to calculate the other angle that I have on my figure.